Welcome to another unit in this workbook, Statistics. This time I'm going to talk about measures of contingency. Measures of contingency, that's like the pronoun for the correlation coefficient, the rank correlation coefficient, but in this case for nominally scaled variables. So the starting point for the calculation of these measures of contingency is the contingency table or the cross table, which usually looks something like this. Whereas here we have different groups for the first variable, here we have different groups for the second variable. That could be intervals, that could be distinct groups like colors, car names, whatever. Since it's nominal, there's actually pretty few requirements on the different characteristics. Then we have here the absolute frequencies for each of these combinations, and down here and on the right the marginal frequencies for each group. So the values here are actually the sums of all the rows, whereas the values down here are the sums of all the columns. And that's the overall number of observations. Could, for example, look something like this. What mean of transport is used in the different cities when commuting to work? That could be one idea. Well, once we have these tables, the first measure of contingency we could calculate is the coefficient of association by Yule. However, the Yule coefficient can only be calculated for contingency tables like this, so 2 times 2 tables. If we have this, that's more or less something like a determinant of this table, so those two multiplied minus those two, that's a part up here. Then we're going to divide it to this multiplied plus this one. So it's almost the same in the numerator as in the denominator, but in the numerator we have a minus, in the denominator a plus. The big advantage of the coefficient by Yule is that it also gives us a little bit of an idea about the direction, because it could be positive or negative. Positive meaning one direction is more strongly pronounced, whereas negative means the other direction is more strongly pronounced. Well, that was everything on the Yule coefficient, because there's not actually a lot to be done with it. So it's a nice coefficient. It's normalized to the interval -1 to +1, but you cannot do any more with it. So we continue with the most commonly used measure instead, and that's the chi-squared statistic. For the chi-squared statistic, however, we need the so-called expected frequencies first. The expected frequencies we get by taking our table, erasing the stuff in between, and considering only the marginal frequencies. Then for each element, we're going to select the respective column and row sum, going to multiply these two. That's what happens up here in the numerator. And we're going to divide them by the number of observations, the value down here. So we could also think about this as a big rectangle. This is one corner of the rectangle, that's the place we're actually considering. Then we take the two adjacent corners, those two, multiply them, and we divide all of this by the opposing corner of the rectangle. Well, once we have these expected frequencies, we can actually calculate the chi-squared statistic. The interesting thing about the chi-squared statistic, the size of the table does not matter. So it could be of any size, doesn't have to be 2 times 2, could be any size we ever want it to be. That's one big advantage of chi-squared, it's not limited in any which way. Well, this structure also is always the same, it's always actual value, the value as was given in the table before, minus the respective expected frequency, in parentheses, to the power of 2, and then divided again by the expected frequency. Well, that's the chi-squared statistic. That's the most commonly used statistic when working with nominal data, but it has two distinct disadvantages. The first one, well, if I increase the number of observations, I have much more potential for a deviation between actual values and expected values. So in one way or another, we have to correct at least a little bit for the number of observations. And what holds for the number of observations also holds for the size of the table. If we increase the table, there are much more different elements in the table, so we add up much more different terms in the calculation of the chi-squared. So it would also be nice to, in one way or another, correct for the size of our contingency table. And that's what we're going to do next. The next one would be the so-called contingency coefficient. The contingency coefficient is chi-squared divided by chi-squared plus n, the number of observations, and then the square root of this. The contingency coefficient has the big advantage. It's also larger than 0, same as chi-squared, but it's no longer limited by infinity. So chi-squared could take any positive value or 0. Contingency coefficient is limited by a much smaller value. And it considers the numbers of observation. So it corrects in this way for the number of observations. The problem, however, is, well, it has an upper limit, it has a finite upper limit, but the finite upper limit is not yet 1. And it's always nice to have a normalized statistic, because then you can very easily get a reference. Is this close to 0, far away from 0, or something like this? And that's what we get if we instead use the corrected contingency coefficient. Here we're going to multiply the contingency coefficient with this correction factor. Correction factor m divided by m minus 1, square root of this. The m, that's actually also pretty easy and straightforward. We're considering the number of columns and the number of rows. That's those two. That's number of rows, number of columns. And we select the smallest of the two. So if it's a 3 times 5 table, we're going to select 2. And then the m is simply this value. So m is whatever is smallest with number of columns and rows. Well, this has the big advantage, not only that the corrected contingency coefficient now is somewhere between 0 and 1. So we actually have a frame of reference, a fixed frame of reference, constant fixed frame of reference. But we also have corrected in one way or another for the size of the contingency table. So we took care of the second problem we had. Well, that's actually a good way to use. However, the same boundaries we used to determine what's a strong, medium, or weak relation not perfectly well apply for this contingency coefficient. That's why if you work in market research or stuff like this, often you might not find the corrected contingency coefficient, but alternatives. For example, Kramer's V or the phi coefficient. So there's a lot more measures of contingency here. I will, however, for, well, brevity's sake, remain with those we just learned about. I hope you still enjoyed this session. I say goodbye and see you next time.